Hi everyone. I am Blessed Joy Di Deliosa, and I'm here to present now the project that I have made. As you can see on the screen, I have utilized the programming language C++, and then I am here to implement the Regula-Falsi method and Simpson one-third rule. Continuing, let's first discuss what is the Regula-Falsi, just for context. So first, it is also called false position method. Also, it is a numerical technique for finding the roots of a continuous function. So I am sorry if I'm looking at the right part of the screen because I have another monitor for me to see it fully. And then also Regula-Falsi is an iterative method that refines an interval A and B that contains the root by repeatedly evaluating the function at the endpoints and at a calculated false position until the root is approximated to a desired accuracy. So as you can see on the screen, I have here the formula for the Regula-Falsi. So as you can see in here, slope m is equal to delta y over delta x, wherein m sub 1 is equal to m sub 2. So we have now the f of b minus f of a all over b minus a is equal to 0 minus f of b all over c minus a. So cross multiplying this, we will now come up with this c minus v multiplied to f of b minus f of a is equal to b minus a multiplied to 0 minus f of b. With that, we now have the c, or the formula for Regula-Falsi. It is now b minus f of b multiplied to b minus a all over f of b minus f of a. So continuing. Now let's discuss the scope and the limitation of the program that I have made. So first, let's discuss the scope of this program. First is the root finding. So the primary purpose of the program is to find the root of a given polynomial using the Regula-Falsi method. Of course, that's the main purpose of it. Also, it takes user input for the coefficients of the polynomial, the initial interval, the error tolerance if you have, and the maximum number of iterations. So it all depends on you. Second, we have the scope of polynomial function, wherein the program is designed to handle a polynomial functions represented by their coefficients in decreasing order of degree. So this part, I'm going to show you how it is implemented in the program later. So it calculates the function value using the provided coefficients in the current approximation of the root. The third one is that the user interaction. So the program allows the user interaction for entering the input parameters such as the numbers of coefficients, the actual coefficients, and then the initial interval, the A and the V, the error tolerance, and the maximum number of iterations. So it prompts the user to decide whether to run the program again. So this part, I'm going to show you again it later. We're in the program as if you want to start a new one again or want to end or terminate the program. Continuing in the scope, we have next the output, wherein the program outputs the root approximation and the number of iteration required to reach the approximation. And then if the maximum number of iteration is reached, it informs the user or it outputs that thing. So continuing now, we have the delimitation of the program that I have made. So the first delimitation of this is the polynomial functions only, because the program is limited to finding roots of polynomial function. With that, it may not work correctly for other types of functions. Next, all about real roots. So the Regula-Falsi method is primarily suitable for finding real roots. So the program may not be able to handle complex roots properly. Next, the program uses a simple convergence criterion based on the absolute value of the function at the current approximation. With that, it may not cover all possible cases, and users should be aware of this limitation. Next one is a major thing as a delimitation. Keep in mind that this program have the input validation because while the program prompts the user for input, it assumes that the user will enter valid numerical values. So if you have entered any other values such as characters, letters, that's a limited input validation. So entering invalid input may lead to unexpected behavior. So keep in mind that this program assumes that the user will enter valid numerical values. Continuing, the single variable function, because this program is designed to find roots of a single variable, which is x, polynomial function does not support multivariable functions such as having x, y, z in a given function. Also, Regula-Falsi method only. We have that method only for this one because I specifically designed this program just to evaluate the given function for Regula-Falsi method. Lastly is that this program is written in C++ language and may not be directly applicable or compatible with other programming languages. So as a sample of output of this one, we have here, as you can see on the screen, it will first prompt a enter the number of coefficient, and it will depend on the user what number will you have. And then the next sample output, I inputted here number 3, meaning this is the decreasing order of degree. We have 2, x raised to 2, x raised to 1, x raised to 0. So the coefficient for this one, you just have to enter. And as for this one, we have 1. Coefficient for x raised to 1, negative 29. For x raised to 0, or the, what do you call this? Is 198. Wait, the coefficient. Oh, for this one, so I just forgot it. And then enter the initial interval. First, I entered for the letter A, which is 15, and then 16 for letter B. And then it will ask you to enter the desired error tolerance. And then as for me, I have entered 0, and then maximum number of iteration, I just have inputted 100. We're in as long as we've reached the maximum iteration and have the root approximation. So with this one, we now have the root approximation of x is equal to 18. And then after outputting the desired output that we wanted, this program will ask now if we want to run again the program. So entering y will lead us to having this again, and then entering n will lead us to terminating the program and having different number letter or invalid input. It will prompt an invalid input and ask us to enter something again. So let me show you the demonstration of the program. So as you can see, we have here the Regula-Falsi. I believe you can see my screen. So we have the Regula-Falsi method program that I have made. So there. So first, let's focus on demonstrating, and I will show you how the program works later and discussing the actual program. So let's demonstrate it first. Running the program now. So let's just wait. So there, as I have told you earlier, we will have the prompt of enter the number of coefficients. So let's just now try it. If I wanted it two coefficients. So x raised to 1 will be 56. Then this one will be -10. This thing is just a sample. So I'm just entering anything. But later I will show you a sample wherein we've answered it in our activity, and we will compare the answer of this program to the activity that we have made. So interval A, let's say it's 2 and then 3. Enter the desired tolerance. Let me say, let's just have the 0 and then maximum number of iteration. So so for this one, we've come up with the maximum iteration reach, and then the root approximation of x is equal to 0.178571. And then, as I have told you earlier, it will ask you if you want to run the program again or no. So let's just type anything. So it says invalid input and asks you to enter something again. Then let me try again. So invalid input again. So if I type y, it will prompt to a new execution of the program. It will start again. So enter the number of coefficient. Let me just try again to show you that we've executed this program with different inputs. So having, let's say, 5. So x raised to 4 is 9, -56, 20, -5, and then 1,000. Interval is, let's say, 5 and 6, and then tolerance, let's stick to 0, and then the maximum iteration that I want is just 100. So having to reach the maximum iteration, the root approximation for this is x is equal to 4.71874. So again, it will ask if we want to run a program again. If I want to end it, just say N or no, then it will exit the program. So now I will test it. That is depends on the activity that we did in Regula-Falsi, just to make sure that the program is working well, and the output that it is that the output that was created by this program is indeed accurate. So let me just clear my screen, and then let's run again the program. So there, so I have run it now. So let me show you first on my screen the activity that we did last time. Actually, it's in the week 3 part. So here it is. Sorry for the lighting. So now we have the um sample function with x raised to 4 plus 10 x raised to 3 minus 4021 or 4021 x raised to 2 or x squared plus 56,800 x plus 29 or 292,000. So let's implement this one. And again, this is the formula that we have used. As you can see on this approximation, we've used the A and B, or the interval 47 and then 48. So we should have the root approximation of 47.0179226631. So going back here, let me just put it here for a while for me to see. Let me run it here. So how many coefficient do we want? So we want 5. So x raised to 4, based on the given that we will use, is that it is just 1. I think it is good if I show you it in the manner of like this. So there. So we will need to solve for this one. So x raised to 3 have the coefficient of 10. So we're just focusing this one. X raised to 2 have the coefficient of negative 4,021. And then for our x, we have 56,800. And then for the last coefficient, we have 292,000. So entering it, again, the initial interval that we have is 47 and 48. So entering it, 47 and then 48. Enter the desired error tolerance. So as per our last activity, let me just show it to you. Review 0 for the desired error tolerance. So let me just enter 0 and then maximum iteration. Let's say we'll just have 100 just to make sure. So the maximum iteration reach root approximation, we have x is equal to 47.0179. Let's check if we have the same output. So we have this, based on this one, we have 4 decimal places. So this is the 4 decimal places, 47.0179 and then 47.0179. With that, we can conclude, or I can conclude, that the program that I have made is indeed accurate. So now, let me just end it for me to discuss the whole this one. So let me discuss it to you. So yeah, discussing now the program language and the actual program that I have made. So let's now first focus on this one. This is the header and namespace declaration wherein we've included these statements. The vector. So vector is used for the vector container, such as the coefficients. And then for CMAT, we've used it for the mathematical functions such as this one. Let me show you. The POW or PO is a power, meaning it's something like x raised to 4, in the degree power 4, like that. And then using namespace STD, we've used this because if we did not include this one, we've need to include it in every C in or C out. So for example, in this one, we've need to declare it as STD colon C out. So we need to show it and input it like that. But having this statement, we can now freely just input and use the C out and C in name. So next is the function to evaluate this one is a function to evaluate the polynomial. As you can see, this function takes a vector of coefficient representing a polynomial in decreasing order of degree and value of x. As you can see in here, this is that part, decreasing value of x. So that's the function to evaluate the polynomial. What is the polynomial that we will be using? Next is the Regula-Falsi method implementation. This function is that one. So as for this one, the function that we have implemented is again Regula-Falsi method, finding the roots, and then we have this formula in finding the root. This one is just the same with the formula that I have shown you. XP is our B and XN is our A. So you can check it if you want, and it is just the same. IT is the iteration. We have the X new or the C, and then coefficient. So this is just depends on what coefficients that you have entered. So yeah, if this formula is less than 0, we will have the XP is equals to X new. Otherwise, the XN is our new X new. So it will repeat, while the ITE, this one keeps on incrementing for us to know if we have reached the maximum iteration. So on the last function, we will see the main function we're in. On this one, this includes the user interaction, input validation, loop continuation. So loop continuation is this one. If we still want this one, if we still want to keep on trying or terminate the program, this one is the validation of input. If it is Y or N, otherwise it will output an invalid input. And then on this one, this is the inputting part. On the first part, like this one, entering the value, and then just mainly all the, what do you call this? All user interaction. So that's all for Regula-Falsi. Now we've, we're going to go to, so let me just close this one for a while. Let's go now to Simpson one-third rule. So again, we'll continue on going with the flow like that. Let's just have the context. What is the Simpson one-third rule? It is a method for numerical integration. And then Simpson one-third rule is something that approximate the integral of a function over an interval a and b again by dividing the interval into an even number of subintervals and using a quadratic polynomial to approximate the function on each subinterval. So based on the handout that we have the formula for Simpson one-third rule as h over 3 multiply to f of x0 plus 4 multiply to f of x1 plus f of x2. So the a is x0. Oh no, it's just continue. So it depends. So going back. So this one we have in our handout how to compute it. But in our program, you just have to enter a and b, the x0 and the x1, and if you have subintervals of 12 like that, the x2, x3, x4, and so on and so forth, um it, the program will calculate it itself. So now going to the scope and the limitation of the program. First, the scope. So the main function of the program is, of course, to calculate the result of integration using the Simpson one-third rule and display the result of it. Next, the program is designed to perform numerical integration using Simpson one-third rule. And then this one, it takes input from the user for the lower limit of integration, the x0 or the a, and the upper limit integration, the x1 or the b, and the number of subintervals if you want it just 2, 4, 6, so on and so forth. Continuing, we have the program checks whether the number of interval is even. So because as Simpson one-third rule requires an even number of sub-interval, if the input is not even, it displays an error message and terminates the entire program. Next, the program provides an option for the user to run the integration process again with different input values. So it is just the same logic that we have in Regula-Falsi. Also, just an addition right now for scope, I forgot to include it here. It also just covers the C++ language. So implementing it in different programming language, the program might not be suitable. Going to the delimitation of program, first, the program is specially designed, again, for numerical integration using Simpson one-third rule and does not support any other integration program. Also, the function of x in the program represent the mathematical function to be integrated as this one. So this formula, e raised to sine x over x raised to 3 minus 10 multiplied to x squared plus 4 is the formula that we have used in the previous activity that we did in week 8. So the limitation of this program is that you need to manually input or change the function that must be done directly in the code. Meaning, in order for, if you need to change the function, for example, I just want to answer the function of x squared plus x, and then I need to remove this from the code and then input the x squared plus x. So I will show it to you later. So that's one of the delimitation of this one. Because unlike to the regular fallacy that we have, whatever that you wanted, how many coefficient that does you want? On this one, it is not just simply like that, because we have now the sign, the exponent, I mean the e. This is the just the letter e, or the exponent function. So this is much more complex. So I designed it so that if you have even more complex function, you can just input it here and then run the program. Next, the program assumes that the users provides valid numerical input. Again, just like in the Regula-Falsi, the program assumes that the lower limit, the upper limit, the number of subintervals that you have input is indeed correct. So it does not handle cases where non-numerical or invalid input is provided. Continuing to the delimitation, the program does not include error handling for potential mathematical issues such as division by zero. If you inputted zero or in the function that was given, this program will not handle it. That's one of the delimitation, or other singularities in the function. Next, the user is prompted to enter Y or N to determine whether they want to run the program again. Any other input is considered invalid, and the user will be prompted again until valid input is provided. So lastly, the program does not include graphical representation or visualization of the integration result or anything like that. So it focuses solely on the numerical calculation and display of the result. So we now have the sample output of this. So enter the lower limit, for example. So inputting the lower limit of 0.10 and then the upper limit of 0.30, then if whatever subinterval that you want, and then immediately the result will be given. Again, the function that was used in this program is mainly stated and manually stated by me, by the user. So if you want to replace it by different function, you just have to change a specific part on the code, and I will show it to you later. So that's it. Do you want to run the program again? Yes or no? And we'll have invalid input. So not now. Let me show you and execute the program. So for a while. So yeah, where is it? So this one, going back to this one. So as you can see in here, we now have the program that I have made for Simpson 1/3 rule. And this is it. The formulas. So this is the part that I have told you. This is the function of exponent sine x. Let me show it to you in our handout. I think this thing is now invisible. So as you can see on this part, this is the function that we need to evaluate. So I just use this one so that when I check the output value of this using the program that I have made, I can show you that it is validated using the activity that we have made. So again, I just want to put the emphasis that if you want to change the function, it is okay. This is the only part that you need to change. So that's one of the delimitation of this program. So let me remove some of it. So yeah, I will discuss it again, the program, later. So now let me just run it for you to see how it is executed. Again, we're just gonna first try to input different inputs for you to see that it can use different inputs. So 0.1, 0.5, a subinterval of 8. So we have the Simpson one-third rule result of 0.195754 with using the function that I have shown you earlier. So if you want to run the program again, any other thing, invalid input. So y is a valid input. So yes, we want again. So 0.6, 0. Let's say 60, even number of, so it says here that it is an error. So I misclick it. I have input 1, but I was supposedly to enter 10. So yeah, again, it's an error. So meaning the program will terminate. So let me run it again. So let's just wait. So another input to try 0.95, 0.98, and then subinterval of 10. So we have the output value of negative 0.015476.2. Do we want to try again? Let's input other characters, numbers. It is an invalid input. If we wanted again to try, so we are allowed to try 0.96, let's say 16. So we have the value, then trying the n for no. So it exited. So let me just clear, and then I will show you the comparison of it to our activity. Let's run it again. So while running, I'm sorry for that. So we have this week 8. Um, sorry. So there. So we now in the Simpson one-third. We have the lower limit of 0.15 and upper limit of 0.45. So let's input that 0.15 and then 0.45. And then enter the number of subintervals. So on the first thing that we did, it is just 2. So input 2. So the output is 0.1387.03, and let's check if it's the same in here. It's 0.138703 because this is 6. So the 2 becomes 3 now. So there. So another example, yes. To validate this again, let's use the one-third with 12 sub-intervals. So with the same, what do you call this? Lower and upper limit, 0.15, 0.45, and then we have 12. So the new value is that 0.137954, and we have the same output 0.137954. So I think I have shown you it now. So let's discuss now the entire program. So again, this one is just inclusion of different libraries. So using namespace std, I have told you that earlier. And then for this limits, I just want to show you, unlike on the validating on this one, I have used the library of limits for handling input error. So it is used on this part. So unlike in Regula-Falsi, we've just used while loop just to check having this parameters. But on this one, to show you a different thing, I have used the limits libraries. So continuing, we now have this function that represent the mathematical function that to be integrated. Again, if you want different function to be integrated, you just have to change this part. Continuing, this is the Simpson integration rule part. This is where it goes handle. So implementing the 1/3 rule for numerical integration. So it takes as the x0 as the parameter lower limit, the x1 as upper limit, the n as number interval, h is the subinterval calculation, just like this one. Let me show you this one. And then the result is initialized to f of 0, f of x1, and then the for loop is the one that calculates the sum of the function values at odd and even index within the subinterval with approximate weights. So the final value is now multiplied by h over 3. So that's how it goes. The same, it is just the same on the formula that I have shown you earlier. So going to the last part is the main function. This is the main function. So the main function includes again the user interaction rather. This is the user interaction part. The limit testing. This is just the what do you call this? Checking if the input that you have entered in the subintervals is even number. So again, this part will now ask again, what is your choice? And then this is where we have used the limit library that we've used and then have the loop, while loop, not until you choose other letters. Still, we have the parameter of this one, but we have different syntax because we've used again the limits library. So that's all for the project that I have made. Again, just a minute. So again, I am Joy D. Deliosa, and this is the project that I have implemented using the C++ language, implementing the Regula-Falsi and Simpson 1/3 rule. So thank you, everyone. That's all.